Thank you very much, Einat. It was really impressive. I just want to say, if somebody has a specific question, just let us know, and the lecturers will try to answer. And I think it's especially impressive, given, showing the broadband of Tel Aviv University, and even though the small size of Israel, our successful rate, and now we want to go to the real science, one of the first real scientific examples. And it's my really big pleasure to invite Professor Ehud Gazit, the former chief scientist of the Ministry of Science and Technology, and the chair of the Biotechnology and Neurodegenerative Disease, and not enough, he is a faculty member of both the Department of Molecular Microbiology and Biotechnology and the Material Science, and the Faculty of Material Science. And that's, I think, explains the topic of his lecture, Nanotechnology, from biomedicine application to advanced materials. Udi, please.
I wanted to be mentioned as scientist, so when before I find my presentation, well, it's not. I should say, I would start with a little bit of personal words about the relationship to the European Commission. So, just from the beginning of my scientific career, at the turn of the century, when we came back to the university, there were not such big startup grants. So the reason that I could establish a quite active research lab was the fact that in the fifth framework, I'm a veteran in those mechanisms, I got a very nice grant in Israeli terms, which allowed me to bring my lab, and then we continued to the sixth framework, the seventh framework, hopefully in Horizon 2020. And in my government position, I was very much involved with the discussions that were before the signing of this very late night discussion with the Prime Minister on the phone, and I'm very happy that we signed this agreement, and I think that it's good for Israel. It's also good for Europe, and I'm very happy about it. So a little bit about science. So as I said, we've been involved in scientific research in both the fifth framework, sixth framework, seventh framework, hopefully Horizon 2020, and the things that we do are related to nanotechnology, and more specifically, we're interested in trying to understand how molecules interact to form ordered structures at the nanoscale. I will use a scientific jargon, but then I will try to explain it also in layman terms, so bear with me. I'm trying to do multi-level presentation. So we are interested, as I said, in molecular self-assembly of biological and bioinspired supramolecular entities. Don't worry about the supramolecular. We are interested, as I said, to understand a little bit sociology of molecules, to understand how molecules interact with one another to form various structures of non-covalent bonds, means that they don't change their basic nature. Our approach is reductionist. We are taking complex molecules, cut them into smaller and smaller pieces, and try to understand what is the smallest piece that can allow the formation of the structure. This is what led us to very small structures. For the biologists or chemists in the audience or listening to us in the internet, peptides and even amino acids. We extend it also to non-biological organic building blocks. So we come from biology and then we extend it to other fields. And we can get all kinds of architectures at the nanoscale. Nanostructures, things that are a millionth of a meter, and our claim to fame is the ability to form all kinds of structures that you know from the macroscopic world, also in the nanoscopic regime. So, and our concept is self-assembly. And as I promised, we start with the science, and then we'll get somewhere to explain it in more layman terms. So we are interested in non-covalent interaction, the way that molecules interact with one another without changing their properties. We're interested in molecular recognition, how one molecule recognizes another one to form all the structures. And this is it relates to a field of supramolecular chemistry put forward by the Nobel laureate Jean-Marie Lehn from Strasbourg. And we are basically interested in all these interactions that lead to the formation of the structures and how we see it, all this understanding all these interactions. So all of you are familiar with Gulliver Journey. And one thing that was realized is the fact that by those very many little notes, you can get a giant object into the ground. So we are trying to understand the chemical interactions that lead to the stabilization of these structures, which are like these little notes that keep the giant into the ground. So it's an ensemble of many, many notes, and this is in a nutshell, if you are not a chemist or a biologist, what we try to identify, all these different structures. And so now I explain what is a non-covalent interaction. We're interested in moving from monomers, single units, to larger structure, oligomer, understanding the molecular recognition process, how molecules interact with one another to form other structures, understand these supramolecular polymers and copolymers. And one thing that we also try is bring concept of polymer chemistry, which was the most important subject in material research in the 20th century. All of you are familiar with nylon, Dacron, PVC, plastic, so on and so forth. We are trying to make these nano, if you want, nano Teflon, nano Kevlar, nano nylon, and others. So bringing concept of polymer chemistry into nanoscience. And this is where it leads us. So this was a paper published in Nature Communication recently with Cambridge University, in which we were able to show that a reductionist approach, leading to very simple structures, even if you are not a chemist, just with high school chemistry, you remember that this is relatively very simple, and it can form all kinds of different structures at the nanoscale, all kinds, nanospheres, nanofibers, nanotubes, and like with polymers that I mentioned, we can get what we know in polymer physics as phase diagrams, that getting all kinds of structure in different domains. And again, it's a nice collaboration with the UK, which get quite a lot of notice by the scientific community, published in a good journal, and explain in a way the things that we're interested in. On the other end, on the other extreme, and this is how is it relevant to really questions related to human health. So I was discussing the self-assembly of very short building blocks, which resemble the polymer size, and much larger structures that are also built by self-assembly. Organization of one molecule tied to another by molecular recognition, sociology of molecules, getting into the formation of the structure, is the formation of viruses. So viruses are being formed by the assembly of different structures and the assembly into the variant that could be infective. Again, without getting into all details of the science, by using crystallography, understanding at the molecular level how these structures are being formed, we are able to develop new ways to inhibit the formation. So you see from very tiny material-like things to relatively large, still at the nanoscale viruses, we could get to different structures. One thing that I'm really interested in, and this is related again to human health, is the formation of nanofibers that are related to disease, amyloid disease. these amyloid structures are formation of nano structures that are being formed in various degenerative disorders, including Alzheimer's disease, Parkinson's disease, type 2 diabetes, ALS. There are many disorders in which there's the formation of these nanofibers. And we are trying to understand how these structures are being formed. I already introduced our main concept, which is reductionism and molecular recognition, how molecules know each other, self-assembly, how they're organized, and we try to put all of this to understand. Again, I will give the scientific and less scientific explanation, and our interest was trying to understand what is the basis for the recognition and self-assembly of these structures. So I think that all the terms were defined, and now to our reductionist approach, which I already mentioned in brief. So starting with relatively large structures, going to smaller ones and smaller ones and smaller ones, we're able to identify the shortest structures that can form these assemblies. We systematically analyze these structures to really to pinpoint what within the structure is important for the formation of the structures, and this led us to understanding mechanistically how it's found and finding a way to control this process, namely developing drugs that can interfere with this process of self-assembly, as I mentioned with the viruses. And this is a list of structures that we made. I want you more to look at the different diseases that are related. So type 2 diabetes, Alzheimer's disease, thyroid carcinoma, and things that are more distinct, but more rare, but you can appreciate what is the meaning of these structures. And what we're able to do, and this is very schematic representation, we're able to identify how these structures are being formed and identifying that aromatic structures, these hexagons that some of you may be, if you're not chemist or biologist, may remember from your high school chemistry, rigid structures that can stack one on top of the other to form ordered structures. And this is something that we put forward already about 10 years ago, and we get a lot of structures supporting this organization of these aromatic structures or hexagonic entities from many groups around the world. I'm moving very fast on a lot of scientific work, but and we are now interested in ways, after understanding this structure, developing all kinds of drugs that, again, without understanding chemistry, just from my description, you can understand. We have, for example, in this case, we have these hexagonal structures. It binds to the recognition interface that we identify, but do not allow further growth because of its structures that you see here. And our Danish connection, you can compare it to Lego building blocks. So only in a specific orientation you can get the formation of the structures. And some of our inhibitors that are being made are like the Lego building blocks, but without the parts above it. So they can bind on the one end, but do not allow further growth of these structures. So we play with Lego building block, another of nature. In the second part of my short presentation, I would like to tell you, again, very briefly, how we moved from these structures into new materials, which brought us to fields of manufacturing with mechanical properties, optical properties, piezoelectric properties of the structures. So I told you about the reductionist approach. We were showing that smaller and smaller structures can form all the nanostructures. We identified the shortest element that can do it, and we wanted to find, going from Alzheimer's disease polypeptide, to find the shortest peptide that can form these structures. In a paper published in Science already more than 10 years ago, we identified probably the shortest element that can form ordered structures at the nanoscale, these nanotubes, which even got the attention of the New York Times, but also of Science magazine. Basically, again, you could see it here. We are very glad to identify such short elements that can form ordered structures, but not only that we're happy about the ability to form this structure, we get all kinds of very unique properties, physical properties. So mechanical properties, these structures that are formed by just mixing some molecules in the pot can form very rigid structures. These spherical structures that we made are again made of mixing molecules by molecular recognition and self-assembly. I already mentioned this concept. So you just mix in the pot the molecules somehow by molecular recognition, by sociology of molecules, know each other, interact, form these spherical structures, and they found to be as stiff as steel, which is probably has to do with the identification of the elementary building blocks to form very unique structures. Found the piezoelectric properties of these structures similar to the best piezoelectric materials that were known before these structures. We found semiconductive properties. Again, I'm moving very fast just to give you the flavor of what you can do with molecular self-assembly of very simple structures when you identified the most fundamental building blocks. And luminescence of the structure, so it's mechanical, piezoelectric, semiconductive, optical properties, and all of this based on the structure. And now we are very happy that many groups around the world are studying those structures that we identified. The minute that you know that you invented something that of real essence is the fact that it appears on a cover of a journal without that you even know it. It's just a group from China wrote a review on this structure. So I think for us, we are very happy that we are spreading this message also beyond the European and the Israeli boundaries. Other things that we are interested is one thing is to make nanostructures. The other thing is to arrange it into order arrays. So in this case, we're able to make what we call nanoforests, so thousands of nanotubes on the tip, on an area like a tip of a pin, by growth, by inkjet printing, by vapor deposition methods. So we apply all kinds of industrial methods to arrange these structures, and this could lead to all kinds of application. We can make, as I mentioned already, all kinds of architecture, also spherical structures, all kinds of different assemblies. And quite recently, and it's also got quite a lot of attention, and again in collaboration with groups in France, the UK, and our neighbors from Israel, we're even extending the boundaries of molecular recognition and self-assembly to very interesting creatures which combine properties of proteins together with DNA. Again, just to give you a flavor of this, we're able to, and this is crystal structure, it's not a model, we're able to make what was a dream until now. It's making something that will be like these hexagonal structures that are stacked on one on top of the other, but also that will have the structures like many of you are familiar with the double helical structure of the DNA. So it has hydrogen bonding, so the way that DNA, the knots of the Gulliver of the DNA that stabilize it together with the stacking that we described in the with the other structures. So and it also gets us to all kinds of very interesting physics. The structures are semiconductors. They have all kinds of colors in the full range of the spectrum, and we're now trying to explore this for industrial application. Just to finish, we're trying to, so dipeptides are very short, but we try to go to even shorter structures. And we studied amino acid, again, aromatic ones, and we discover that the shortest aromatic structures, which is phenylalanine, can form these nanofibers as I described before, which is related to a metabolic disease that many of us are familiar with just by consumption of calorie-restricted drinks. So if you read and you drink Diet Coke, you read it contains phenylalanine, not for PKU patients. So we discovered the mechanism, and again, I don't have the time or some of the people in the background, the scientific background to explain it fully, but we provided new mechanistic insights to a metabolic disease that was known for many years, but was not fully understood. And again, this was in collaboration with Zurich University, not in the European Union, but a member of the program. Again, this a little bit of, I'm still insisting to show the crystal structure. Yes, I'm going to finish it. Showing us how these Lego building blocks are being formed. So this is, of course, work of many students, and this I like the most, our periodic chart. And if somebody is interested in the original work, very welcome to read it. Thank you.